Welcome to the Bioinformatics Chat. This is another one of my solo episodes, although I have some great guests lined up for the next few episodes, so stay tuned. And before we start, I want to tell you about a conference. It's called Integrative Biology and Medicine. It will take place in the beginning of October in Kiev, Ukraine, and a lot of great speakers and scientists are coming from all over the world to Ukraine to share their ideas and present their work. For example, Nikolaus Rayevsky, who is famous for his work on circular RNAs, will present some data from loss-of-function studies in mice for two separate circular RNAs. Basically, we're still mostly unsure what their function is, and Nikolaus will explain our current understanding of this phenomenon. So be sure to check it out, integrativebio.com.ua. You will find the link in the show notes. Register, and I hope to see you there. I was recently reading the Sailfish paper. Sailfish is an RNA-Seq quantification tool. It was the first tool that performed RNA-Seq quantification without any alignment. So later, tools like Callisto and Salmon followed. To be clear, Sailfish evolved a lot over the time and it borrowed the algorithms from the other tools. But when I refer to Sailfish, I refer to the very first version that was described in the preprint and in the paper. So instead of doing alignment, Sailfish relies on the k-mers, and it needs to quantify k-mers and store k-mers efficiently. And for that, it hashes them. It applies a hash function to turn a k-mer into a small integer number. So this is not news. Hash tables have been around for a long time. But Sailfish uses something called a perfect hash function. The difference between a perfect hash function and an ordinary hash function is that an ordinary hash function will likely to have collisions, whereas a perfect hash function can map all k-mers into unique small integers. So then instead of manipulating k-mers, you can manipulate these small integers and not worry that you then will be unable to map the integer back onto k-mer. So let's think about some of the ways this hash function can be implemented. If we are allowed to add new elements, then no perfect hash function can ever exist, because eventually we will add more elements than the range of the hash function even allows. So for example, if the hash function maps our k-mers to integers from 0 to 200, they can only accommodate 201 k-mers. So if we eventually add 202 k-mers to our hash table, or try to hash 202 numbers with our hash function, then there is no chance that this function could map these 202 numbers onto 201 unique integers. But in Sailfish, we don't need to add new k-mers because we index the fixed transcriptome and we collect all k-mers from the transcriptome, and therefore we know in advance how many distinct k-mers are contained in the transcriptome. So we can in advance pick the range of our hash function to accommodate all these k-mers. So if we know the k-mers in advance, let's say there are n k-mers total, how can we build a perfect hash function? Well, we could just enumerate all the k-mers, right? So we take the first k-mer and assign it number 0, the second k-mer, assign it number 1, and so on. So you need some fixed ordering of the k-mers. And you could sort them lexicographically in the alphabetical order, in the dictionary order. Doing so has two advantages. Well, first you have a fixed order so that you know for sure which k-mer corresponds to number 5. This is the 5th k-mer in your lexicographically sorted list. The second advantage is that you can map the k-mer to the number very efficiently because we can do binary search. If we have a k-mer that we want to map to an integer, then we look right in the middle of our list of all k-mers. If our k-mer is lexicographically less than the middle one, then we further look into the first half of the list. If it's lexicographically greater than the middle, then we look further into the right half of the list. And so we can move every time halving the table, the list, and we can find out the number corresponding to a k-mer in log n time. So log n time is much better than linear time, but it's still not constant. So the question is, can we map k-mers to numbers not in logarithmic time, but actually in constant time? And this is, of course, what hash functions do, because they're functions. They can be computed in constant time, or at least sort of a time proportional to the length of the k-mer, but independent of the total number of k-mers. Another shortcut approach we could take is use an ordinary hash table. An ordinary hash table may have collisions, but those collisions are hidden inside hash table. So if we assign each k-mer a number and store this mapping in the hash table, so not use the hash itself as a number, but store the correspondence between k-mers and numbers in a hash table, then this gives us amortized constant access time. But what if we are not happy with amortized constant time? What if we want to go further and say we actually want worst case constant time? And a hash table cannot grant us this, because a hash table, remember, it has collisions, and all the collisions in this case do not affect the correctness of the mapping. They still affect the worst case time. So here's an idea. What if we could generate random hash functions? Okay, how could we do this? Well, this could be done very easily if we have a single hash function that maps k-mers to integers. Then we could add some fixed string in the beginning of the k-mer. Okay, so whenever we want to hash a k-mer, before hashing we add a fixed string at the beginning. Let's say we add AT to every k-mer before hashing. Then this will be also a hash function, which is completely different from the original hash function. That's the property of hash functions. If you slightly modify the input, the output is changed drastically and unpredictably. So in this way, by varying the prefix that you add to the k-mers, you can manufacture basically an infinite amount of hash functions. Of course, the prefix shouldn't be too long, because then this would affect the time that the hash function takes to compute. But as long as you stick to short prefixes, you can generate new and sort of random hash functions. So here's the idea. What if we just keep generating hash functions, and for every hash function we see whether there is a collision or not. And if there is a collision, then we go on to the next function. We basically generate new random functions until we find one that on a given set of k-mers that we want to hash, on it has no collisions. Ultimately, we will find such a function, right? Because obviously these functions exist. There exists a function from n k-mers to the numbers from 0 to n-1, such as each k-mer is mapped onto a unique integer. So if we try long enough, we will find such a function, hopefully. Unfortunately, this can take simply too long. Why is that the case? Well, these functions that have no collisions, they are extremely rare. This is known as the birthday paradox. Imagine we want to find a group of n people where every person has a unique birthday. So the birthday in this case acts as a sort of a random hash function. If we pick the group at random, then if a group contains just 100 people, then the probability that there will be at least one collision is 99.9999%, right? It's a huge probability. You can pretty much be certain that there will be a collision. And notice that there are just 100 people and there are 365 different hash values, right? So we are not even close to n. It's n over 3.5, and still the probability of collisions is incredibly high. To get to a 50% collision probability, you have to go down to 23 people. So the same holds for our random hash functions. If we want to hope to find a good or even perfect hash function in a finite time, then the range of our hash function has to be much larger than the number of k-mers that we hope to hash. And much larger in this case means that the range of the hash function has to be of the order of n squared. So if we want to hash n k-mers, we need about n square hash table, a hash table of size n square, the order of n square, to hold our mapping. And this is, of course, a high price to pay because the number of k-mers we're thinking about is huge. And if we square it, it's going to be incredibly huge. So this naive strategy of simply generating new random hash functions and waiting until we just stumble upon a hash function that just works for our SAT is not realistic unless we're willing to increase the range of the hash function. But let's go with it for a moment. Let's increase the range of our hash function to the order of n squared and find this perfect hash function. So it allows us to map each of the n k-mers onto a number from 0 to an order of n squared, such that every k-mer maps to a unique integer. Now, how can we reduce the storage requirements for this hash table? So to remind you, the hash table is needed to provide a mapping from the numbers from 0 to n squared minus 1, let's say, to the numbers from 0 to n minus 1, right? So we want to map n numbers. And remember, we have just n numbers because we have n k-mers. But the range of these numbers are from 0 to n squared minus 1. So we want to compress n numbers that can take values from 0 to n squared minus 1 to n numbers that can take values from 0 to n minus 1. Imagine a square table n by n rows and n columns. And the cells of this square table correspond obviously to the numbers from 0 to n squared minus 1. So you can imagine that our numbers from 0 to n minus 1, these are the numbers that we want to map to. These are the unique identifiers for our k-mers, that they are written in the square table in the cells that correspond to the values of the hash function. So hash function maps k-mers onto the cells of the square table n by n, and in the corresponding cells to which the hash function mapped the k-mer, we write the index of that k-mer that we would like to assign to that k-mer. Of course, the square table still takes n squared space to store. But what if we could not store it, but instead calculate the number in the cell based on the cell's row number and column number? Let's see how we can do that. So let's take the first k-mer. It is mapped somewhere in this square table, and we have a certain row number, certain column number, and a certain number that we would like to assign it. Let's say 0. We want to assign it number 0. Our strategy will be to assign certain numbers to rows and columns separately. So every row has some number, Every column has some number associated with it that we assign. And then we will assign them in such a way that the number written inside the table, that's the index that we want to assign to the k-mer, that number is the sum of the row number and the column number, modulo n, okay? So we add the row number and the column number, take modulo n, and that's the index of the k-mer that we're assigning it. So we look at the first k-mer and the cell in the table that corresponds to the first k-mer, and we say we want to assign it number 0, so we will assign its row number 0, and we will assign its column number 0. So that our property holds for this k-mer. For this k-mer, the row number plus column number equals the desired index number, 0. Let's see if there are any other k-mers that were mapped to the same row number or column number. Why does this matter? Because if there are no other k-mers assigned to this row number and the column number, then the numbers we assign to the row and the column just don't matter. So we can assign pretty much anything and we will get no conflict. So what we're worried here is the conflicts. And the conflict arises when for one k-mer, we need to assign one set of numbers to the row and the column. For the other k-mer, we need to assign the other pair of numbers to the row and the column. And those two are in conflict. So if there are two k-mers on the same column, and to retain our property that we can calculate the k-mer index based on the column number, to retain that property, we need to assign to the column number 1 for the first k-mer and number 2 for the second k-mer. That wouldn't work because now we have to assign two different numbers to the same column. That's not what we want. Therefore, after we assigned the row and column number for the first k-mer, let's look if there are any other k-mers in that row or on that column. Let's say there is a second k-mer mapped on the same column. Now we can no longer vary the number we assigned to the column because it was fixed when we consider the first k-mer, but we still have the unique row for that k-mer. Okay, and we can subtract from the index of the second k-mer the number assigned to the column, and we get the number that we should assign to the row of that second k-mer in order to retain our property. So we sort of solve this equation and get the number that should be assigned to this second row. And then we repeat this procedure. Now, are we certain that we will never get any conflicts? Not yet. We cannot be certain because we can eventually come to a cell for which we need to assign, let's say, column because its row was fixed on the previous step. The number assigned to its row was fixed on the previous step, so now we have to assign its column. But its column has also been assigned on some earlier step. Okay? So both its row and its column has their numbers assigned on some earlier steps. Now what does this mean? This means that we made a cycle on this table. If we consider the cells of this table as a graph, as vertices of a graph, and we connect the cells that have the same row number or the same column number, then we can only get a conflict trying to assign numbers to rows and columns only in the case when there is a cycle on the board in this graph. So if we got this cycle, then it's pretty much game over. We have nowhere to go from here. But we can simply declare this hash function that led to a cycle as a poor hash function for this data set. And we go to the next random hash function. And we can iterate until we find a hash function that produces no cycle on this table. And so naturally we need to ask, how likely is it that we will get a hash function that will result in no cycles on the hash table? It turns out that if we perform these calculations, that the probability we will get an acyclic graph is a pretty good probability. So if we try a few times, we're pretty certain to arrive at a random hash function that will produce no cycles in this table. And so we can create an assignment. We can assign the numbers to rows and columns so that every number written in the table, every k-mer index, can be computed from the row number and the column number. So now, how many numbers do we have to store? We have to store every number we assign to every row and every column. There are n rows and n columns. There are 2n numbers in total that we have to store. So our space requirement is on the order of n, and not on the order of n squared as we feared originally. This is a huge improvement. So this is pretty much the strategy that is taken in Sailfish. We can generate random hash functions until we arrive at a suitable hash function that can be encoded in space of 2n approximately. It maps every k-mer onto a unique number from 0 to n-1, and the lookup takes constant time, because for the lookup to happen, we simply compute the hash function, we translate the hash function onto the coordinates, onto the column number and the row number of the cell in the table. So those are simple arithmetic operations. Then we'll look up the column number and the row number in their own tables, and we sum up the two numbers. So this is the constant amount of arithmetic operations. So there you go. Now you know how to manufacture a perfect hash function.